Hello all, I'm Ramesh and we will be seeing about the assignment 2 problems in this video. So the content is basically the modeling of the problem, how I approached it and the coding and the results of this. So I was given two problems and the problem one is about a layer of viscous fluid flows down a vertical plate. So you can see the image. So this is mainly driven by the gravity, and this is the plate, also known as wall. And the main condition is the density of the fluid varies linearly from rho 1 to rho 2. So the main point is rho 2 is less than rho 1 at y is equal to b. So this varies linearly, and we have to find the velocity distribution and the velocity at the free surface. So the way I approached it is uh, the assumptions are steady flow and it is fully developed and there are no flow in y and z directions, so there is no pressure gradient. The flow is mainly driven by the gravity because it is a vertical plane, and the boundary conditions are velocity is zero at the wall, so this is a no slip boundary condition, and velocity will be maximum at the free surface, so the gradient will be velocity gradient will be zero. So based on the given uh, uh, condition that density varies linearly, so from the classic straight line equation, y is equal to mx plus c, so we can derive the equation for rho as a function of y, and we get this equation. So for deriving the equation for velocity, x momentum equation is considered, and from the assumptions it is reduced to this. So since we don't have pressure gradient, and these will get cancelled out since study, and rho is a variable, and we will get this. So u is a main function of velocity is a function of y direction, so we get this rho gx by mu. Mu is dynamic viscosity, gx is the acceleration due to gravity, and rho is the density. So based on the equation we got for rho in the previous slide, we substitute for rho and integrate it twice. So we get this equation with two integral constants, c1 and c2. So applying the boundary conditions and solving for c1 and c2, we get this equation for u of y, and the velocity at free surface can be found when we substitute y is equal to b, because it is the free surface. And so this is the MATLAB code I have generated. Since there are no values given in the problem, I have assumed these values for the sake of coding and plotting. And the this is input parameters, and the velocity distribution can be coded in the form of for loop, because I have spliced the width of the flow to 100 points, and from a for loop we can calculate the velocity at each point, and the velocity at free surface can be calculated from the direct equation. So when we non-dimensionalize the velocity and velocity with maximum velocity, we get this plot. So this is what we expected. So since the flow is vertical in nature, so the flow velocity will be zero at the wall and maximum at the free surface, and it varies parabolically. So yeah. So this is the problem two, and the problem two is a planar Couette flow, and is being generated between the two parallel infinite parallel plates, and the plates the upper plate is moving with the velocity u. So the variation based on the normal Couette flow is the fluids are there are two fluids inside between the two parallel plates. So these are two immiscible viscous liquids, and we have to find the velocity distribution in the two liquids. So the modeling is basically similar to what we saw in the previous problem, and flow is assumed to be steady and fully developed and incompressible. there are no body forces since it is horizontal, and there will be no body forces in the flow, and there are no flow in y and z directions, and no, there are no pressure gradient. It is not mentioned in the question, and the boundary conditions for this is, since we have two fluids, we will get four boundary conditions, and at y is equal to 0, u2 is 0. The downflow, the fluid two's velocity is taken as u2, and fluid one velocity is taken as u1, and the fluid one is above the fluid two. So at y is equal to h, u1 is capital U, the velocity of the plate itself. And at y is equal to d, d is the distance of fluid from the base plate to the fluid one's width. So at d, the both the velocities will be same. So the fluid one and fluid two's velocity will be same. And at y is equal to d, the shear stress will also be same. So we take this boundary condition. So it is also similar to the previous problem. So from the x momentum equation, we reduce it based on our assumptions, and with the integrating twice, we get u1 and u2 as a function of y. So applying the boundary conditions to get c1, c2, c3, and c4, we get these two equations for y is equal to 1 and y is equal to 2. Y1 as a function of y, and u2 is a function of y. So u1 is basically the fluid one's velocity. U2 is basically the velocity of second fluid. So fluid one is varying from d to h, and fluid two is varying from 0 to y. So the MATLAB code is these are the input parameters. Again, there are no values given in the question. So I assumed the values. So these are all in SI units, and mu1, mu2 is the dynamic viscosity of water and engine oil. So these are taken from the internet, and use the maximum velocity of the plate. So based on these assumed values, a code is written to calculate the velocity of velocity at each point in the fluid. So this is a basic for loop, and for calculating the velocity at fluid one, fluid two, and this is the calculation for fluid one, because the this we can order it anywhere. Any this can be put up, and this can be put down. It will not make a difference. So this velocity plot is also non-dimensionalized, because from the value of Umax. So as you can see, this is the fluid one's velocity profile, and this is uh, the velocity profile of fluid two. As you can see, the maximum velocity is here, as the plate is this fluid particle will be in contact with the plate, moving plate, and the maximum velocity will be here. So this appears like a straight line because of the mu. Again, when we play with these mu values, we can get a, a velocity profile accordingly. So yeah, this is the uh, explanation of problems for assignment 2. Thank you.